So last lecture we discussed about the use of translation look aside buffer, which is a cache memory, which has some sort of associative registers wherein parallel search is possible, which results into effective access time. Okay, so two variables we have used: epsilon, which is the associative lookup time, which is less than 10% of memory access time, and the hit ratio. That means the number of time or percentage of times that a page number is found in the TLB. That is the hit ratio, or rather I can say cache hit ratio or TLB hit ratio. Oh, multiple words are used for that. Now the formula I already given there. Now it is actually very simple thing. Now if you just concentrate here on here, if you look at, let me use different color there, this one. Now this calculation is very simple. When we say 80%, it is 0.8 because it is 80 divided by 100, right? So 0.8 multiplied by 100 plus 0.20 multiplied by 200. Now why 200 is very simple thing. We need to access the memory twice if there is a TLB miss, right? So that is 200 multiplied by 0.20 because that is the lookup part is required, and that gives you like 0.80 multiplied by 100 plus 0.20 multiplied by 200. That gives me 120 nanoseconds. But again, that is just example, but more realistic hit ratio is 99%, and reason I mentioned, because whenever the TLB miss happens, when page is not there in the page table, in the cache rather, then such a page will be fetched there. And if the page size is say just half KB, so 512, so there will be TLB miss only for once, and remaining 511 times there will be TLB hit. So that is the reason, like 99% of the time TLB hit will happen, and for that realistic figure of 99% TLB hit ratio, the effective access time results in 101 nanoseconds. So just one additional nanosecond is required. Okay, so that is effective access time that we have discussed yesterday. Now let us continue our discussion of paging with respect to memory protection. Now first of all, what is memory protection? See, memory protection is something like whether we want to permit the access or privileges for reading, for writing, or for execution. So these kind of bits can be added to each frame, indicating whether you have the read-only access or read-write access, or maybe simply execute only. Execute only is typically required whenever you have instructions stored in the frame. Okay, so that kind of additional protection can be also provided. Now valid invalid bit can be attached to each entry in the page table. So this is also one more additional bit, whether that frame is valid or not. Now whenever you say it is valid, it indicates that the associated page is in the processor's logical address space. You may wonder why it is required. So for example, maybe the page table is larger than whatever the number of entries in the page table are there. So for example, a process needs 4 pages, and maybe page table is having some sort of 10 pages, something like that, or 10 entries in that. Okay, so that is one of the implementation. So in that case, what happens is only first 4 are valid, right? Only first 4 are valid. So that will be indicated by this bit, valid or invalid. Anyways, that we see in the next figure. And once, if it is valid, access to those addresses will be legal. Whenever it is invalid, this indicates that the page is not in the processor's logical address space. That means page is there in the page table, but that is not part of the address space of the process. So this is one solution where we can have multiple entries or more entries than the entries in the page table. Or another thing could be something like we need to have something like PTLR, page table length register. That means, for example, rather than saying first 4 entries are valid and next remaining are invalid, better option is the PTLR will hold the value of 4, indicating that first 4 entries are valid and rest entries are not valid. The same trick we use in case of segment table length register also. Okay. So if CPU tries to access the page which is invalid, that will result into the trap to the kernel. So trap is like non-maskable interrupt, so that will occur, and then operating system may terminate that process, saying that something like segmentation fault, where you are trying to access the memory to which you do not have permission or which is not part of your logical address space. So that kind of memory protection is provided. Still, there is one problem in this case. Imagine something like 1000 is the page size, and process needs something like 1200 bytes. So 2 pages will be, or 2 frames will be allocated there. That means as per valid and invalid bit, what will happen is first 2 frames will be valid, or even in case of PTLR, the length is something like 2 pages. That means first 2 pages are valid. But then still the problem is, for example, if process want to access, or a process is trying to access memory address something like say 1300, even though that page is valid, that is not the address space of the process, because process's address space is up to 1200. But because the page size is 1000, 2 pages have been allocated. Okay. So this kind of errors need to be handled by, again, the operating system. See, this is the valid and invalid bit in the page table. So previously in the page table we have just frame numbers for appropriate page number, and page numbers are used as a lookup index there in the page table. Now that V indicates that, now for example, if you see the process, there are total 5 pages, 0 to 5, total 6 pages are there. Okay. So if total 6 pages are there, now first 6 pages like 0, 1, 2, 3, 4 and 5, the valid invalid bit is set to V. V stands for valid. Whereas for 6th and 7th, it is marked as I, invalid. Now here our assumption is a page table will have 8 entries and process needs just 6 pages. So definitely now the problem can be solved by 2 approaches, either using valid invalid bit, or like I mentioned, PTLR, page table length register. So PTLR will have the value of 6. That means first 6 pages are valid and next is invalid. Okay, so that is how we can utilize the valid and invalid bit in a page table. Now, like segmentation, we can share the segment. I remember I mentioned the example of the square root function. So square root function, maybe library function or maybe user defined function, doesn't matter. A separate function will be in the separate segment, and if that function is being used by multiple processes, a single copy will be there in the memory, and that can be shared. On the similar lines, shared pages concept is also possible. Okay, and this is typically required for the code part. See, what is there in the process? We have data and instruction. So instruction is the code part, right? So instruction never change. Okay, we never change the instruction part. What is changed is maybe data part will be changed, right? So we can have and this shared code is typically a read-only code. That is the reason we never change it. So for example, suppose there is a text editor. Assume that a time shared system is there where multiple users are attached to the system, and assume it's something like one lab is there and 20 students are making use of that VI editor. For simplicity, let me take example of VI editor, right? So VI editor is being used by all 20 students to write program, maybe in C language, C++ language, doesn't matter. Okay, and that computer is time shared. So assume that there is one page for data. That is the private code, and that data is actually getting modified. And the editor's code, that is read-only code. Okay, and suppose that needs some sort of 3 pages for editor code and 1 page for data. I think that we'll discuss in next slide. It is there, but first of all, we need to understand what do you mean by read-only code. Okay, when we write a program, say for example, in one terminal I use VI editor, in another terminal I use VI editor, and in one more terminal again I am using VI editor. So VI process is actually, or VI program is actually executed 3 times, resulting in 3 different processes. But whatever the code that implements the VI functionality, it is read-only code. We are not modifying it. Right? Now what will be modified? Whenever I save the file from VI, that data part will change. So remember that data part is your private code and data, whereas the actual program, maybe it is text editor, maybe it is compiler, maybe any executable thing. Okay, so that is the shared code. Okay, so that becomes exactly same like multiple threads, they are sharing the same processes space. Okay, that could be used for inter-process communication, where read-write pages are allowed. Whereas when we talk about the data part, what happens is whenever I save the file in first VI editor, say something like server.c, then client.c, and something like header.h, something like that. Okay, so when we save it, that is fine. That is your private data. Maybe you need separate page for that. The same example is mentioned here. Suppose this is process 1. So this is one process, okay, wherein 3 pages are used for editor, assume it is a VI editor, and just 1 is private. So this one is shared part and this one is private part. And if the same is executed, assume that this data is something like abc.txt or a.txt. So this data is a.txt. Okay. So my command is something like vi a.txt. For process 2, it could be vi b.txt, and for process 3, it could be vi c.txt. Now what is changing in all 3 is a.txt, b.txt, and c.txt, and that is my private data. That is private data of that process. Whereas what is common in all 3 is vi, the program, that is the editor, which is used to actually modify a.txt or b.txt or c.txt. So the program is same. Okay. Now just assume that only one process is there, process P1. So 1, 2, 3, and 4 pages are there. Maybe ED1, this is the page loaded at the frame 3. So it gives me 3. The page table for process P1, it says it is 3. Now ED2, which is the editor's page 2, is loaded at the frame 4. So that is reflected in page table. Editor's third part is loaded into the frame 6. So page table entry is updated. And whatever the private data, now this is not shareable, right? This is private data. So that is loaded somewhere here at frame 1. So page table is updated. So now for process P1, 4 pages are required, and for every page 4 frames are required. Up to this it is fine. Now comes the concept of sharing or shared pages. Now suppose user has used the command something like vi b.txt. Now vi editor needs 3 pages as usual. ED1, ED2, and ED3. These 3 pages are required there, right? But these 3 pages are read only and they are already loaded for process P1. Can we utilize it? Ritul, Nakil, B39, please mute yourself. Now for process P2, ED1, ED2, ED3, they are exactly same like process P1. And remember that process P1 is not going to modify those pages, ED1, ED2, ED3. Why? Because that is editor's code. You are supposed to modify your data and not editor's code, right? So ED1, ED2, ED3, these 3 pages are already there in the memory. So no need to upload again. No need to reload it. So ED1, which is already at 3, ED2, which is already at frame 4, ED3, which is already at frame 6, will be shared now. Okay. And this data 2, which is the private part, this is loaded at the frame number 7, so it is updated in the page table. And same thing is repeated for process 3. So 3, 4, 6, which are for ED1, ED2, and ED3 are shared. And this private part, data 3, which is loaded in the frame number 2, that is just updated. So logically speaking, process P1 needs 1, 2, 3, 4 pages. Process 2 needs 4 pages. Process 3 needs 4. So 4 plus 4 plus 4. Total 12 pages are required. But if you actually see the memory, just 6 pages are utilized here. Why? Reason is very simple. Data 1, which is private, data 2, which is private, data 3, which is private. So 3 different frames are required for data 1, data 2, and data 3. Right? Whereas 9 pages are required for editor. Why 9? 3 for P1, 3 for P2, and 3 for P3. But rather than using 9, pages are shared here. So ED1, ED2, and ED3. ED1, ED2, and ED3. That is frame number 3, frame number 4, and frame number 6. These frames are shared amongst all 3 processes, P1, P2, P3. Got it? So like segmentation, sharing is also possible with the pages. Now we need to see the structure of page table. Okay, actually in depth part is given here. Number B39. Unmute yourself.
Of net connectivity and coming problem.
Net connectivity problem. But that should not create problem with mute and unmute, no?
But here getting I'm problem.
105 frames are there. 105. And because of your net connectivity problem, you are saying it is muting and unmuting.
Sir, I'm rejoining again and again. That's why it is occurring problem.
See, in my setting, should I share my settings there? In my setting, what I mentioned is mute on joining. Just change the setting. Okay. Now let us continue. The structure of the page table we are discussing. Sometimes see what happens is with the modern operating system and with more memory, especially whenever the addresses are something like 32-bit or 64-bit, then implementation of paging is not straightforward. Reason behind that is very simple. Let us consider one example. Suppose we have a 32-bit logical address. Suppose we have a 32-bit logical address, which is nowadays very common thing. So total address space will be 2 raised to 32. So those many memory locations will be there. Okay, 2 raised to 32. And let us assume that the page size is 4 KB. Okay, the page size is 4 KB. Now 2 raised to 10 is 1 KB, right? 2 raised to 11 is 2 KB and 2 raised to 12 is 4 KB. That means if you remember this part, if total number of bits are 32, this is typically divided into something like this, where these 12 bits are used for offset. Why? Because my page size is 4 KB, right? So remaining 20 bits are utilized for what? The page number. That means those many entries will be there, maximum I'm saying, of course, those many number of pages will be there. And do you know 2 raised to 20 is like 1 million entries. 2 raised to 20 is 1 million entries. 1 million is like your 1 MB, I can say. Right? Now, if the page number is represented by, say, 4-byte integer, because anyways 2 bytes are not sufficient here, because like byte character data type, short integer is 2 byte, integer is 4 bytes, something like that. So at least 4 bytes are required in order to represent the page number. So if 4 bytes are required for that, and if 1 million entries are there, 4 MB, because 4 bytes are used to denote this, no? So 1 million entries multiplied by 4 bytes, that gives me 4 million, that is 4 MB. So 4 MB of physical address space is required for page table itself. Can you imagine? 4 MB. Okay. So that creates a problem. Why? Because up till now what we have seen is page table is stored in contiguous space. Now talking on the same line, if 4 KB is my page size and 4 MB is size of anyways maximum, but still we need to do that calculation, size of my page table, how many pages are required for page table itself? Yes, do it fast, do the calculation. Page size is 4 KB and page table size is 4 MB. How many pages are required? Yes. Rajvardhan Aditya, you mentioned correct. 1024, exactly. So 1024 pages are required to store the page table. Can you imagine that? And do we have that much of space available contiguously? See, from contiguous memory allocation, we switched to segmentation. What was the reason? We cannot assign contiguous memory. That creates so many problems. Okay. So we switch to segmentation, and even fine grained part will be given with, like, for example, to avoid the external fragmentation, we shifted to paging. But here for page table itself, we need something like 1024 pages contiguous, right? So what is the structure of this page table? So three solutions are provided for this. One is hierarchical paging, one is hashed page tables, and one is inverted page tables. Now what happens in case of hierarchical paging is we can break up the logical address space into multiple page tables. Meaning of that, say, for example, we cannot allocate complete process at a single place. So we divided the memory of process into different pages, and the entry of these pages will be in the page table. Now what we want to do here is we want to divide the page table itself. So multiple pages will be utilized. So that definitely creates a kind of hierarchy of page table now. Okay. So meaning of that is we page the page table. See here. So now this time we have two page tables. One is outer page table, one is inner page table, and then direct access to the memory. Okay. So it is something like this. So actual frames will be denoted in the memory. Then the page table. Now this is page of page table, and then we have outer page table. So that is like two level, and this can be even further divided with like 3-level page table scheme also. Okay. So the logical address in this 2-level paging becomes something like page number will be denoted by P1, P2, and then offset is by T. So my logical address, which is say 32-bit machine with 1K page size. Now 1K, reason behind this is this will utilize now 10 pages, 10 bits. That will be divided into 22 bits for page number and 10 bits for page offset. And again, because this 22 bits is too long, we further divided it into something like 12-bit page number and 10-bit page offset for page table. So this hierarchy, like first upon outer page, so P1 will be the index in the outer page, P2 will be the index into the inner page, and then the offset. What is the optimum size for offset? No, it is not for offset. See, optimum size will be decided, I think yesterday also I mentioned the same part. Optimum size will be decided by nature of the programs executed on that operating system. If very small programs are there, then it will try to fit the complete process into the multiple of that page size. So I think yesterday I given example, two page sizes are utilized by Solaris. One is 4 KB and one is 8 KB and another one is 4 MB. So that will be decided by the designers of operating system. Okay, looking into the heuristic data, something like what results in better performance. Then it will be decided. Now here you can do one thing on Linux operating system. There is one command called as getconf, getconf, getconf. Okay, something like this. If you fire this command getconf page size, you will get what is the size used by that operating system. So that is decided by the designers of that, right? it is not necessarily. Here we see that size of P1 is greater than P2. Is it? No, it is definitely not necessary. Whatever the 22 bits are there, it could be 12 plus 10, it could be 11 plus 11, it could be 10 plus 12, doesn't matter. That doesn't matter. Only thing is we need to have some sort of two-level paging because one level itself is huge. Okay. And this is also called as forward map page table. So for example, you can check it here. Whatever my logical address is there, P1 is used as an index in outer page. Now from that, we'll get the base address of page table, wherein we'll make use of P2 as an displacement or index or lookup. Again, from that, we'll get the base address. That is typically the frame number. And then D, that is used as displacement as an data or instruction for that process. So it is just like one hierarchy is added here. Now that was just example for 32-bit. Now 64-bit processors are also available nowadays, right? With 64-bit logical address space, even two-level paging scheme is not sufficient. Okay, maybe 3-level, 4-level. So the same idea, it is like what happens in case of a pointers in C. Like a normal variable is there whose address can be stored in a pointer variable, but address of that pointer variable can be stored in another pointer variable. So that is something like int star star p. Third level of indirection is also possible, where we can store address of pointer. So such a pointer is something like int star 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 p, something like that. So like that hierarchy we can increase. Okay. Now this is again, as I mentioned, just example. Now page offset is 12. What is mentioned here is page offset in this diagram is 12. What is the page size? Simple thing, it is 2 raised to 12. That definitely gives me 4 KB. So this is 4 KB. Inner page, yes, we can have something like this. Again, is it 42 plus 10? Because again, when we say 42, so 2 raised to 42. That gives me the size of the outer page table. So maybe this 42 is also divided. So that is the like 3-level hierarchy. Idea behind that is again same. So now, for example, 42 plus 10 plus 12 can be again further divided something like 32 plus 10 plus 10 plus 12. Now this time we have inner page table, then outer page table, then second outer page table. Okay. Concept is again same. So that was the first way of structuring the page table, where we can have hierarchy. Second part is hashed page tables. Now, I guess you already aware of hashing data structure that is used to map it. Okay. Hashed page tables are typically used whenever the address space is greater than 32 bits. Okay. What happens in that case is whatever the virtual page number is there, that will be hashed into a page table. Hashing is one of the searching techniques in data structure. You can imagine that as an key, some sort of hash function is implemented onto that, and rather than searching sequentially or even binary search, with single stroke, will directly map that key to its value. That is what the hashing is. So that idea can be used here, wherein the page table, it will contain the chain of elements hashing to the same location. So if the same entry is mapping to the same table, I guess that is called as a collision in case of hashing, right? And in order to solve the collision, maybe second hashing is used or chaining is used. Now, typically it is chain of elements mentioned in this. Here each element contains the virtual page number the value of the map page frame. So page number is there, then the map page frame is there, and it will having pointer to the next element. That will have some sort of chain of elements hashing to the same location. Now for comparison, the virtual page numbers are used there. So if there is a match, the corresponding physical frame will be extracted directly. If there are several pages, in that case, you need to look for in the chain. So rather than looking at all the addresses sequentially, first level of this is like hashing is used, and then if multiple or several pages are mapped to the same thing, we need to look up for that in the chain. So that is what hash page table is. So for example, whatever my page number is there, logical page number, some sort of hash function. So it is not like searching one by one, then second, then third. No. We'll make use of hash function. It will map directly to the frame number. Now, if this is unique, we'll directly get it. If it is not unique, now this kind of stuff will go. So now this is called as a chaining. This part is called as a chaining. So here you need to have some sort of sequential search. From that, we'll get some sort of address. That is the best address. Plus, make use of this P as an displacement in that, and then you'll get the actual physical address for that. Okay. So this is called as hash page table. And third technique is by making use of inverted page tables. Now, see, normally with each and every process we have a separate page table. Now this is exactly reverse of that. This is exactly reverse of that. Rather than making use of page table for each and every process, okay, what can be done is we'll have a single page table which will keep track of all possible pages. Okay, and like previously we have a process, then we locate the page table of that process, and then from page table we'll get the thread. Here what happens is exactly reverse thing will be done here. For example, we'll have a page table common to all. We have a page table common to all. Okay. Now whenever you are looking for some page, we need to do lookup on the process first of all. I think there is a diagram for that. Yes. Now have a look at this. Have a look at this. Okay. Now this is system-wide page table. Remember, try to understand the difference here. This is system-wide page table. Whatever the page table we have seen till now is per process page table. But now this time it is system-wide page table. What happens is only one page table is available there. Okay. Now in the logical address, one more thing is added, and that is the process ID. Now PID is unique. Now we'll do lookup for this PID, for example this, and then we'll look for the page number. From that we'll get some sort of frame number here, and here remember frame number is used as an index. That's it. You're getting it now? Like previously we are making use of P as an index there, right? Now this time it is not the case. Here we are searching for the process ID, and then there is a P. So page number P for that process, and now this displacement will be used as the frame number there. And then this will be added with the offset, and you will get the physical address. So this is the inverted. This actually saves some sort of space there, but again there are problems with that. And these problems are, for example, what happens in case of a shared memory. Okay, because with shared memory we have a separate page tables, but then whose PID to put there? For example, if there is a page, say frame number is 25, and that is a editor's frame number, and the same is utilized between three processes. So three processes will have three separate PIDs. How to use that? Right? How we can utilize the TLB? Because previously what I mentioned is the process which is running, page table of that will be loaded into the TLB. Now because we have a single page table, we need to load some part of that. But again in that case, we never know that the contiguous pages are there. Okay. So how to load it? Even though it decreases the memory required to store each table, like per process page table, but it definitely increases the time required for searching. Whenever you are referring to any of the data or instruction for that process. So these are three different ways. Now I guess this is end of now. This is just some examples. That is end of this unit. Now let me share. Okay, before moving forward, let me summarize it. We started our discussion with the logical memory and the physical memory. CPU generate addresses from the logical address space, and then what happens is whatever addresses that can be seen by the processor are all just logical addresses. Physical addresses are managed by MMU, that is memory management unit, which is a hardware part of operating system. Always remember, those addresses are not at all available for us. And very simple reason for that is that whenever we have a relocatable code, now we see in different type of bindings also. Static or compile time, load time, run time, where we can bound some sort of addresses. And then how the processes are loaded into the memory. Now for that we saw three methods majorly. One is contiguous memory allocation, that also with fixed partition or variable partition. Then we saw something like segmentation strategy, and then we saw paging strategy. Okay. Remember, even though all these three things are there, still one limitation is available, and that is we cannot execute partially loaded process. What do you mean? Say for example, if 34 KB are required for process, until and unless complete process is not loaded into the memory, we cannot start execution. And this part will be allowed with the help of virtual memory. Anyways, that we'll see in the next lecture. Even though you can see the end of main memory now, because this is a textbook slides, because as per our syllabus, this is not end of unit number 5, because virtual memory is also part of this. So that part will start next time. Now I want to just share one thing, which is the ISE component for you. So let me share the browser. Yes, can you see the browser? I just opened the Moodle operating system course. Okay, fine. Now, can you see this highlighted part? ISE2, I mentioned poster design. Okay, so let me explain what you are supposed to do in this. I just want to explain what is this. As an ISE2 component, one of the ISE2 component. Say for ISE1, I already taken that quiz 1, and our first assignment, Linux. Let me close this. Okay. This first assignment, study of basic Linux commands. If anyone has still not completed it, you are supposed to upload it, because that I'll consider as a second component for ISE 1. Okay. And for ISE 2, this is the poster design. Now let me explain what to do in this poster design. Now, because I logged in as teacher, different phases are there. Forget about that. Now, instruction I mentioned for this is, let me go to edits, or let me change my role to student so that you will see how it looks like this. Okay. So you are supposed to design the poster, say maximum up to 2 pages. Let me move to the topics part first of all. So this is for your poster design topics. You are supposed to design a poster or a kind of a cheat sheet. I think, do you know what is cheat sheet? Anybody? It is notes kind of a thing, where one example also I added there. I'll explain that also. So for example, say scheduling algorithms, because that is one of the topic there. Now we know that we have studied 3-4 different CPU scheduling algorithms, right? Process scheduling algorithms are there, like first come first serve, then shortest job, SRTN, round robin, priority based. Okay. Now we'll keep the key points. If diagrams are there, yes, you can put diagram also. So those part or those stuff will be available on a single sheet. Okay. It is kind of a small notes you are making for yourself. Okay, for example, in our department, all the departmental information will be available on single page, like how many staffs are there, how many faculties are there, how many labs are there, what is the total investment, what are other infrastructure, what is our placement. So we are not giving in detail information of this. So for example, placement, we usually say like 90% of the students are placed with higher package of 7 lakh, something like that. Okay, it is kind of a highlights, looking at which will get some sort of insight about that. That is what the poster is, or cheat sheet is. Okay, where we store our information in compact form. So you are supposed to select any one of the topic. 5 topics I mentioned there. One is process scheduling, multi-threading, semaphores, classical problems of synchronization. These are actually producer, consumer, dining, philosopher, reader, writer. Okay, inter-process communication. Yes, inter-process communication with shared memory, IPC with message passing. So many, whatever the mechanism, pipes are there. So you select any one of the topic, and then you are supposed to design your poster or kind of a cheat sheet, not more than 2 pages, and upload it. And whatever you are uploading, it should be in the format of PDF or JPG or PNG. Now, say for example, 2 pages are there. Now PDF can have 2 pages, no problem. But with JPG and PNG, you may upload 2 separate JPGs and PNGs. Okay, so that way you can upload. Now, the assessment strategy used for this will be peer assessment, where 70% marks you will get for your submission and 30% marks you will get for evaluating others. So that means randomly I'll pick students and assign it to the assessment. Assume that 10 students are there, so 10 submissions are there, and suppose everybody needs to be evaluate 3 submissions. So what will happen is your submission will be assessed by 3 students. That is the peer assessment. And then teacher assessment means myself and Petkar sir. Okay, both will also assess the same thing, and average marks will be given. Now whatever the marks given for evaluation by you will be checked against the teacher's average. Let me tell you one example. Suppose I am supposed to give marks out of 10, and purposefully or by mistake, suppose you given 10 marks, 10 marks, 10 marks for all 3, 10, 10, 10, right? And suppose I have given something like 8 marks, and suppose sir has given something like 5 marks. So average of 5 and 8 becomes what? 6.5, right? 6.5, and actually you have given 10 marks just without checking. Suppose you given highest mark 10 marks. Now average comes to 6.5, right? So if it is 6.5 but you have given 10, how long you are from the average, those many marks will be reduced from your grade. So if 30% marks are there, and suppose that comes to something like 10. So if you give 10 for evaluating work of others, now you are supposed to evaluate 3 students, and your submission will be evaluated by 3 students. In addition to that, teachers. This is basically called as a peer assessment. Peer assessment, where you are assessing the task submitted by your friends. Okay. So assess the work of others sincerely. That is one thing. Second important thing is the topics I already mentioned. Okay, no problem. Let me go back. And now I want to go to the students view. So switch role to the student. Okay. So these are the instructions for submission. So design your poster or cheat sheet on any one of the selected topic. You are not supposed to select multiple topics. Just select only one. It should not be more than 2 pages. File types for submission is PDF, JPEG or PNG. It should be attractive and with meaningful technical content. You can make use of tables, then text, different fonts, drawings, images. That thing can be added there. Okay. For assessment, for example, I have given something like VI cheat sheet here. Okay. Now you simply open this. It is being downloaded. I think I need to share it again. So let me stop sharing this and let me share it with you. Where it has downloaded. On a desktop, it is there. So let me share this part. Share it. Can you see this? Yes, can you see this? Okay, fine. So like, for example, I use simple text there, but I try to make it attractive. For example, how to use the VI editor. So how we'll create, what are different modes are available, what are different commands are there. So there are 2 pages. So this is one of the cheat sheet. For example, this is just for your reference. Not necessarily you need to replicate similar kind of thing. Now, like for example, this don't contain any what I can say, diagrams, drawings. Okay. So that is how it works. And for assessment, let me again go back and share the browser. Okay. Assess example submission. How you are supposed to assess is something like, let me move to my normal mode and let me show you the instructions for assessment. Assessment will be based on three things. Okay, and these three things are the three criteria I have given there. Anyways, when you submit it, you are supposed to give marks on the scale of 10 points, and three aspects I have mentioned. One thing is sufficient technical information. Second thing is whether it is attractive. So look and feel like good fonts, good font sizes are used or not. And third thing is the mistakes, like spelling mistakes should not be there, grammatical errors should not be there, something like that. Okay. Important thing is the timeline. Follow all the timeline because it will automatically move from one stage to another stage. So for example, submissions are allowed from, right now it is allowed, no problem. Last date is 11th of November till 4 p.m. 11th November till 4 p.m. And automatically it will switch to the next phase, which is the assessment, for which I have given 2 days. So 11th November, like it stops at 4. Assessment will start at 4 immediately, and up to 12th of November. There is question from chat. How to choose the topic? It is your choice. Okay, like for assignments, I have given some sort of formula to calculate key. No, this time you can select any topic of your interest. Is that clear?